Hello, everybody, and welcome to MME 2305 Material and Energy Balances. The title of this lecture is Energy Balances Part 3, so it's the third lecture and also the final lecture for talking about non-reactive energy balances. I'm the professor, Dave Robertson, and I can be reached at drobertson@utep. Kind of recapping what we did last time, we did a change in enthalpy in a closed system and we used an electric arc furnace. So the change in energy of the systems plus the change in energy of the surroundings is equal to zero. There is no pressure volume work. So the change in internal energy equals negative change in work. So all the heat that was put into that electric arc furnace came from the electric current. One of the things that we were doing is it wasn't quite a real world situation because we were assuming that there was no heat loss. The reason why our value ended up being positive is because the electricity supplied to those electrodes was essentially coming from somewhere else. So it was work being done to the system. We saw in the previous slide that the change in internal energy equaled negative delta W. Negative times negative is a positive, so that's why we're dealing with positive values. And if you want to refresh what I'm talking about, just please go look at lecture number 2. So now I'm proposing that we take a look at an isolated system, and I'm really happy about it. Here's a painstakingly drawn PowerPoint picture depicting a block calorimeter. Block calorimeters are pretty important because they are how sensible heat is measured. You take a material you don't know the sensible heat of, you drop it into this block calorimeter. It's an isolated system, so there's no heat lost, so no heat's leaving the system. All the heat is dropped into this device, which has a copper block, so we know the sensible heats of copper. So any temperature change, we can figure out how much energy went into the copper to cause that change in energy, and then we can figure out the sensible heat. So the change in temperature of the copper block is measured, and we can calculate the sensible heat. And we're going to do that right now. So here's an example problem. So we have alumina, Al2O3. In this problem, we have 1 gram of alpha alumina. We're dropping it into a well-insulated calorimeter block, which consists of 1 kilogram of copper. So we know how much copper there is. The initial temperature of the alumina sample is 2000 degrees Kelvin. So we're trying to figure out what the sensible heat is of this block at 2000 K. We put it in this block calorimeter and let it sit for a while, and the copper block rises from room temperature to a maximum temperature of 303.4 Kelvin. So all the heat that was in this alumina was transferred to this copper block, so we're assuming no heat loss. So by this process, we can determine what the sensible heat of alumina is at 2000 Kelvin. Or to rephrase it, we want to know what is the sensible heat of alumina at 2000 Kelvin. So this is a recurring theme. We always calculate the number of moles, and right now we're calculating the number of moles of our critical substances. So in this case, it's copper and alumina. We had some givens in the problem. So we had 1 gram of alumina. We know the molecular mass of alumina is 101.96 grams, so 101.96 grams per mole. We can use our railroad track method here, and we can cancel grams of alumina, and we're left with moles of alumina, or specifically gram moles of alumina. So 0.00981 gram moles of alumina is what we're ending up with. Copper, we were told we had 1 kilogram of copper, so a kilogram is 1,000 grams, so 1,000 grams of copper. The atomic mass of copper is 63.54 grams of copper in 1 gram mole. So now we know we have 15.74 gram moles of copper. Now our second step is we want to figure out how much energy it took to raise that copper block from 303.4 Kelvin From the Excel thermodynamic tool, we can calculate the sensible heat of copper. We can use the heat capacity equation. We can use the sensible heat equation. We can also just input 303.4 Kelvin into the table, and we get a value of 128 joules per mole. So the sensible heat of copper is at 303.4 Kelvin is 128 joules per mole. So that's how much energy it took to raise this block from room temperature to 304 degrees Kelvin. We know how many moles of copper we have, so we can calculate the total heat given by this alumina block to the copper block. So we multiply that by 15.74 moles, which is our calculated moles of copper, and we get a total heat or a total enthalpy change of 2014.72 joules. So now we can assume that all the heat was transferred from the alumina to that copper block, and that the alumina cooled to room temperature. So based on that, we can now calculate the sensible heat of alumina is all the heat that came out of that alumina divided by the number of moles of alumina we had. So we get 205,374.12 joules per mole. Kind of talking about where I got the value of 128 joules for copper, I use the Excel tool. When it opens up, you can actually input discrete temperatures. So I put 303.4 and I got 128 joules per mole. And that was actually pretty close. We calculated roughly 205,000, and this is close to 210. So we're a little bit off, but it's pretty close based on our calculation. Looking at the sensible heat table for alumina. The next process we're going to talk about, I have a little mistake on this slide. This should be delta Q equals delta H equals 0. I think it might be cut off or something, either that or I just typed 0. It's an adiabatic process. And to give an example of an adiabatic process, we'll kind of pose this question. There's several metal-based additive manufacturing platforms. There's selective laser melting, selective laser sintering, and electron beam melting, Arcam being the company for electron beam melting. They all use these small powder particles, and they essentially fuse them together with either an electron beam or a laser. And so the question I'm proposing now is, how is the powder for the Arcam and other metal powder bed additive manufacturing machines made? And it's made by a process called gas atomization. And I dare say that Dippin' Dots, formerly known as Dippin' Dots ice cream of the future, I guess the future's finally come, I dare say that Dippin' Dots is made by this same process, gas atomization. In this case, we're dealing with molten metal, not molten ice cream, where we have molten metal flowing into a stream of inert gas, which creates spherical droplets and rapidly solidifies the metal. This is kind of an expensive process. You have to use inert gases. Argon and nitrogen in the N2 form are two common inert gases to make these metal powders. Nitrogen sometimes gives problems, particularly when you're dealing with stainless steels, because nitrogen thermodynamically stabilizes austenite. So there's several research articles and literature with retained austenite and using nitrogen. Before you get too excited about nitrogen, though, we're going to do a problem related to argon, where argon is essentially used as a coolant to help create these spherical droplets from a metal stream. The next problem, we're going to be making hafnium powder, and it's kind of an exotic metal that's kind of finding its way in a lot of applications these days. So we have our problem here. There's our fictional character, Joe Additive, and he wishes to fabricate components from hafnium in his electron beam melting EBM machine. He approaches you about the production of 1 kilogram of powder. So we have some mass here. For his experiments, the initial temperature of the molten hafnium is 2,500 Kelvin. Your atomizer uses argon to create the powder by cooling the molten stream of hafnium to form spherical particles. Your target final temperature for the powder mixture is 310 Kelvin. It's important that you don't expose hot micro powders and nano powders to air because they'll explode. 310 Kelvin is warm but safe enough not to cause an explosion. So now our question is, how many moles of argon will you need to produce 1 kilogram of hafnium? This type of problem is pretty much a combined mass and energy balance problem. It's non-reactive, but it's a combined mass energy balance problem. So we're using basically an energy balance to figure out mass. In this case, it's going to be moles, which we can easily get to mass if we were asked. But we're using energy to figure out how much of a substance we need to carry out this metal processing, processing process. Sorry about that. We're given some important information here. So we have our sensible heat equations. So if we're given sensible heat equations, remember, you do not have to integrate. So we're given the sensible heat equation for hafnium, and we're given the sensible heat equation for argon. And we're also given a bit of information. The sensible heat of hafnium at 2,500 Kelvin is 102.97 joules per mole. It is super, super helpful to diagram these problems out. And by diagram these problems out, I mean, let's go through the thermal cycle. We've seen this before where we were talking about Kirchhoff's loop law or Kirchhoff's law. To get to point A to point B doesn't matter. You're always getting from point A to point B, but it doesn't matter what path you take more specifically. And so let's look at the thermal cycle we're doing for hafnium. So hafnium, we're starting at 250 K and we're going to end at 310 K. But we're using sensible heat. So we will first have to take it to 298 K and then bring it back up to 310 K. That's the process we're going to be following for this class. Argon, we're assuming it's coming in at room temperature, so we're only going to have to bring that up to 310 K. So we'll use the sensible heat equations. We're actually given sensible heat of hafnium at 2,500 K. So this value will be negative. We'll use this equation to figure out raising it to 310 K. And for argon, we're going to use this equation to figure out raising it to 310 K. One thing we don't want to get away from is the heat from cooling the hafnium doesn't go anywhere else. It simply goes into the argon, so there's no net heat exchange, or heat loss, excuse me. It's a heat exchange between the two components within the system. So we look at how we've worked out this problem. I'm going to add some little details to kind of help decode my chicken scratch. As always, the first step is to find the moles of hafnium. You may be asking, hey man, shouldn't we be finding the moles of argon? Well, that ends up being the end solution to the problem. So the first thing we did was we figured out the number of moles of hafnium. It was given to us that we were going to make 1 kilogram of powder. I did my gram to kilogram conversion over here. I probably should have done it first, but we converted to really kilogram moles and then to gram moles by converting from kilograms to grams. So our units all work out. Now we end up with 5.6 gram moles of hafnium. That is good. So we had our diagram on the previous slide. We want to first cool it to room temperature, and so this was the sensible heat of hafnium at 2,500 K, and then we want to raise it back up to 310, and so this was a sensible heat equation of hafnium, and we just plug in 310 K here. So we cooled it from 2,500, that's why it's negative, and then we raise it to 310, that's why it's positive, and we're just taking into account the sensible heat equation that was given to us. We work it out, so we figure out that the heat required to cool this hafnium to 310 is this value. Kind of reiterating, we're cooling from 2,500 K to room temperature. We're raising back up to 310 K using the sensible heat equation. We worked that out. I left it in terms of joules because I wanted to make the units work out correctly when we figure out how many moles of argon we need. But N delta H, so number of moles times the sensible heat for hafnium equals this. So 5,3387.75. Really, if I blocked out this N, it would be joules per mole because we multiplied our number of moles when we worked out the calculation. Now we have to calculate the amount of heat it would take to raise argon from room temperature to 310 Kelvin. And we use our sensible heat equation for argon. We're solving for the number of moles. So it's N delta H argon equals N times what we got when we plugged 310 in. So that's 245.3 joules. N delta H for hafnium plus N delta H argon, or number of moles times change in enthalpy for hafnium, plus number of moles times change in enthalpy for argon has to equal 0. It's an adiabatic process. The heat from this is going to this. Since we cooled our hafnium, it has a numerical sign of negative. We can move that over to the other side of the equation and simply solve for moles of argon. And we get a positive number, which is good because we're looking for a number of a substance. And so I got 2,337.49 gram moles of argon. Kind of to reiterate again, the heat to cool the hafnium must be transferred to the argon, and the sum of that should be 0. Let's take a look at this other problem. It's another combined mass and energy balance problem. We have 1,000 gram moles per hour of a stream of 60%, 40% lead. Hooray, another zinc lead refining problem. We're cooling this stream by passing it through a water-cooled coil. And the initial temperature in the molten stream is 900 Kelvin, and the final temperature of the molten stream is 700 Kelvin. The initial temperature of the water in the coil is room temperature, and it can only reach a maximum temperature of 450 Kelvin, else we're going to break the recirculating pump. How many moles of water per hour do you need? And we're given some other helpful stuff. So we have the sensible heat of water at 450 Kelvin. This is kind of a boundary condition for us because the water can get no hotter or else we're going to break our recirculating pump. If you guys don't know, I run an extrusion lab. I have a water-cooled extruder and I go through pumps, and I should probably do some sort of calculation like this to help me out. We're given heat capacity equations this time, so make note of that. We're not given the sensible heat equation, we're given the heat capacity equation. So if we're given the heat capacity equation, guess what we have to do? We have to integrate. So we're given the heat capacity equation for lead, and we're given the heat capacity equation for zinc. So you remember the change in enthalpy is the integral of heat capacity. So we integrate these equations in the calculation. We'll see that shortly. I drew a flow chart to kind of help us out. And again, this is combined mass and energy balance. It's kind of a simple mass balance because we have one input, one output. We didn't go through any pressure changes or anything like that. We're not told we did. And we're not given anything telling us any indication that there's a different flow rate on the output. So the flow rate going in is 1,000 gram moles per hour. We have our composition, 60% zinc, and we know it's molar. And we know our input temperature is 900 K. Our output is the same, 1,000 gram moles per hour. Still the same composition. We're not doing a separation problem this time. But the key tidbit here is that we're lowering our temperature to 700 Kelvin. And that's kind of important in our calculation. How is this cooling? Where's the heat going? Well, the heat's going into water. The moles per hour is basically dictated by this maximum temperature our water can reach. So that's why it's very, very important. And so all the heat from this incoming flow or incoming stream of zinc and lead is going into this water. There's a limit to how hot that water can get. So that is what dictates our moles per hour. And that's how we're going to go about working out the problem. I've also done a kind of another thermal diagram. I find these to be very helpful again. So the first process we're doing is we're cooling our mixture to 700 Kelvin. To do that, we have to start at 900, go down to 298, and then raise it back up to 700 K. We're not using sensible heat, so we don't really have to go through this rigmarole. I'll show you one of the beauties of actually integrating and doing the heat capacity equation on the next slide. The other thing we're doing is we're raising water from room temperature to 450 K. We don't have to do anything but pay attention to the sign, and it's 11,599 joules per mole is the sensible heat of water at 450 K. So we're just going to raise it up. So let's take a look at how we work this out. All right, so here is how we worked out this problem. The first step is going to be a pretty common step, kind of a recurring theme, as I've said before. Step one, we're going to find the moles of lead and zinc. We were given a basis of 1,000 gram moles. So we said 1,000 gram moles per hour, and we know it's 60% zinc, 40% lead. So that means we have 600 gram moles of zinc per hour and 400 gram moles of lead per hour. The heat of this mixture, I kind of talked about it. The heat's going somewhere. We're cooling it from 900 to 700 K, so this heat's released, and that heat goes into the water. And step two, we want to figure out how much the change in heat was from cooling this mixture from 900 Kelvin to 700 Kelvin. I'm using heat interchangeably with enthalpy. One of the beauties, so we don't have to pay respect to room temperature here because we're not doing sensible heat. We can integrate over the interval 900 to 700, and the math works itself out for us. So we don't have to arbitrarily put a negative sign. So integrating from 900 to 700 of our sensible heat equation, gives us a negative value, and we're also multiplying it by the number of moles. So it's number of moles times the change of enthalpy for zinc, and that gives us 3,765,600 joules. We then do the same thing for lead, and we integrate from 900 to 700, and again, the math takes care of itself and gives us a negative sign. I'm going to get to this next part. The total heat transferred to the water is the number of moles times the delta change in enthalpy of zinc plus the number of moles times the change in enthalpy for lead. We add these together and we get negative 6,151,200,000 joules. If you notice, though, I've highlighted this. We want to say that 6,151,200 joules, is transferred to water. So it's heating up the water, it's going into the water, so it's positive. And I kind of made a little reminder. So it's positive because we heated it up, it's negative because we cooled it. When we use it to complete our calculation, we use it as a positive value. This is another instance where the units of the problem basically have you solve the problem so it kind of works itself out. We start off with joules per hour. We're given the sensible heat of water at 450 K, which is our max temperature. So that's the maximum amount of heat that we can absorb, 11,599 joules per mole. And we just cancel the units out and figure out how many moles of water per hour are needed to make this process work. So 530.32 moles of water per hour. Another problem, and this is the final problem we'll work out today, is another zinc refining problem. We're not going to do the chemistry part. We're going to just do the mass and energy balance part. So zinc can be refined by reacting zinc and carbon monoxide to form a zinc vapor. Carbon dioxide and carbon monoxide. So we react zinc and carbon monoxide, we make a vapor, vaporize zinc. There's also carbon dioxide as a byproduct and carbon monoxide as a byproduct. Again, we're not focusing on the chemistry part. This is still non-reactive energy balances. This is a non-reactive combined mass energy balance. We're feeding this gas to a condenser to get the zinc out. So we're condensing it into a liquid stream, and then the other two gases are leaving in a separate gas stream. To aid in the condensation process, some of the liquid zinc is recirculated back into the condenser to kind of repeat myself, to aid in the condensation process. Not the best written problem, I apologize. Given the temperatures on the flow chart, please calculate the amount of zinc which must be recirculated to make everything work out. I left the values off of this slide for brevity. Let's take a look at the flow chart. All right, so looking at our flow chart, again, this is combined material energy balance. We're looking at zinc refining. We have this input gas. It's 28% zinc, 62% carbon monoxide, and 10% carbon dioxide. That's given to us in the mole percent. We know our input temperature is 1550 degrees C. Instead of assuming a basis, we're given a basis of 20 metric tons per hour of zinc. The condensed zinc comes out at 525 C, as does the gas. This zinc goes off somewhere else and gets cooled further, and some of it's recirculated back at 440 degrees C, but we don't know how much is recirculated back, and that's what we need to calculate. If we look again at our thermal diagram, we're cooling our mixture from 1550 C to 25 C, so that tells us that we're definitely going to be using sensible heats here. We're going from 1550 to 525, but to get there, we have to kind of take this roundabout path. So we first have to cool it to room temperature and raise it back up to 525 C. The recirculated zinc, we know it's coming in at 440 C, and we know it's going to go back up to 525 because it's going to come back out with this condensed zinc. So first we have to drop it to 25 and then raise it to 525 C. And we just got to figure out how much of this recirculated zinc we have to put back into the stream to make this process work. Here's my calculation, and again, I'll kind of decode it. Step one is always find the number of moles, and in this case, our constituents are zinc, carbon monoxide, and carbon dioxide. We were given our basis, so everything hinges upon this basis. 20 metric tons, so tons is spelled this way again as metric tons. 20 metric tons per hour. There is 1,000 kilograms in 1 metric ton. The atomic mass of zinc is 65.38 kilograms in 1 kilogram mole of zinc. I got 305.9 kilogram moles of zinc per hour. Again, for these processes, we're working in the gram mole, so I multiply it by 1,000, so 305.9 times 10 to the 3 gram moles of zinc per hour. Remember, this zinc's in a gaseous state, so we can say it's acting as an ideal gas, so we can use this molar ratio to calculate how many gram moles of everything else we have. So we use the same basis. We use our 28 to 62 ratio of zinc to carbon monoxide to get this many gram moles. Feel free to rewind to look at the flow chart to see where I'm getting these numbers. And we did the same thing again, this time for CO2. We had a 28 to 10 ratio of zinc to CO2, and we got this many gram moles of CO2. I made my own handwritten table. I converted from from degrees centigrade to Kelvin, and then I got the sensible heats off of that Excel sheet for every constituent. So the key temperatures were 1550, 525 C for zinc, carbon dioxide, and carbon monoxide because we cooled everything from 1550 to 525. We then have some zinc coming back into the process, and we're going to raise it from 440 to 525, so we need the sensible heat there. The thing that we need to pay attention to is the heating and cooling. We've kind of seen this on the other problems. So this value, it's cooling from 1550 to room temperature. So this is the sensible heat with respect to 298 K. So that's why it's negative. We then have to raise it up to 525 C to get the calculation for cooling it from 15 to 525. And so step 2, we're calculating the cooling to 525, and it's going through that Kirchhoff loop process. So we calculated the heats for cooling all of our constituents to 525 C. We then add it all together. So the total heat of cooling all of our substances to 525 C is a negative 7.31 times 10 to the 10 joules per hour. And remember, it's cooling it, so that's why it's negative. So this is the enthalpy of cooling the mixture to 525 degrees C, or if you want to work in Kelvin, 798 degrees Kelvin. We then have to figure out what our delta H2 is. Our delta H1 plus delta H2 should equal 0, because this is, again, an adiabatic process. So this heat that was given off needs to go into heating the recirculated zinc. And how do we calculate that? This way. So I copied my table and brought it over here. The entering zinc, it's going from 440 to 525 degrees Kelvin. From an enthalpy point of view, it's going, or from a sensible heat point of view, it's going from 18,754 joules. I got it off my little table here, up to 21,421 joules. So 440 to 525, or if you want to deal in Kelvin, 713 to 798 Kelvin. Again, we drop it to room temperature first. That's why it's negative, and then we raise it up to the 525 degrees C, so that's why it's positive. I did this one a little bit backwards. But that's the heat of of raising it from 440 to 525. This value plus our delta H1 should equal 0. Our delta H1 from the previous slide was negative 7.31 times 10 to the 10 joules per hour. So number of moles times this heat, which we got by basically subtracting this value from this value, should give us 0. We can then move our delta H1, or the heat of cooling the entire mixture, over to the other side of the equation and solve for number of moles of zinc. So we have 2.7 times 10 to the 7 moles of zinc per hour as our answer. This is based on the fact that the recirculated zinc cannot get hotter than 525 degrees C. That's because it's going back into the condensation stream, and we were told in the problem that the condensation stream is exiting at 525 degrees C, or 798 K. Oh my! It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.